Okay, so for this section 1.2.1, we're going to talk about quantitative data. And so a few objectives down here. We're going to make and interpret dot plots and stem plots of quantitative data. We did dot plots a little bit in the first section. So we're going to talk about stem plots. You probably see them, in elementary school throughout your math career here and there, but you may not remember what they are. We'll describe the overall pattern, which is shape, center, and spread of a distribution, and identify any major departures from the pattern. We call those outliers. And then we'll identify shape of a distribution from a graph either as roughly symmetric or skewed. And we'll learn to compare distributions of quantitative data using dot plots or stem plots. All right, so here I'm given a few different distributions. It doesn't matter what the context is, really, but I will give you some context. So two friends are looking to move to a new city. So they look at seven different cities, and their temperatures over various days throughout the year. And so what we have is a distribution graph of temperature for each city. And we're asked some questions about these distributions. So the first thing to ask is, what is the most important difference between cities A, B, and C? So we're just looking at these top three cities. And we want to know about what's their most important difference. One thing we can do is if we trace kind of the general shape of the distribution, we get an idea of roughly what that shape is. We're going to learn later on, this is called a density curve. So we're just looking at the rough overall shape, and they all basically have that same overall shape, roughly symmetric. Now, when we look at the spread of the distribution, just how wide they are, they're all roughly the same width. One might be slightly longer or shorter than the other, but again, we're talking in rough terms here. They look roughly similar. The one difference is their positioning. When I say positioning, I mean if we look at the middle or center of the distribution, they all roughly center in different places at different temperatures. So when we look at the center of a distribution, what we're really looking at is a typical temperature for that city. So they all have roughly different typical temperatures. So for number one, I'm going to say the main key difference is where they are centered. All right, so let's answer number two. What's the most important difference between cities C and D? So looking at C and D now. So if I trace over C, okay, roughly symmetric. D, also roughly symmetric, but in a different way. And the key difference there, if I look at where these ones, how spread out they are, there's an obvious difference, right? If we look at their center, I would say they're roughly the same. They're both roughly centered around here, near 80 degrees or so. But D, city D, there's much more variability in temperatures throughout the year, whereas C is much less variability. So variability is something that we call spread of a distribution. So I would say the spread of temperatures. All right, number three. What are two important differences between cities D and E? So looking at D and E, again, I would say they're roughly centered in the same location. If we look at the overall spread, it seems like they have roughly the same overall spread, and they're both kind of symmetric, both kind of centered in the same place around 80 degrees. But D is much more uniform than E. And so when I say uniform, I mean their overall range is roughly the same, but E seems to have outliers. Whereas D, it pretty consistently has data throughout its entire range. And it has almost the same number of days at each temperature. So we'll say E has outliers, whereas D is much more uniform. All right, and then the last one. What's the most important difference between cities C, F, and G? All right, so now we're looking at C, F, and G. Again, I'll start by tracing the rough shape over the distribution. And in this one, the shapes are all clearly different. C is symmetric, whereas F has a clump of data on the left and then trails off towards the right, and G opposite, a clump of data on the right and then trails off towards the left. So we're going to call that difference the shape of the distributions. All right. And so now we're kind of ready to get these generalities written down. I would write down everything in the yellow box. So how do we examine the distribution of a quantitative variable? So what you're going to look for is the overall pattern and for striking departures from the pattern. And there are kind of three main things you want to look for. That's shape, center, spread. So you want to discuss the shape, the center, and the spread. And if individual values fall outside the overall pattern, those are called outliers, and you want to discuss those. For now, outliers just means anything that clearly departs from the pattern. Okay, so I would say none of these seem to have outliers except maybe E. E seems to have a high outlier and a low outlier, and we just want to discuss those as possible outliers. So remember, in statistics, you never kind of want to say anything definitive. Because we're just playing this by ear, and there's no hard and fast rules for computing when there is an outlier, you're just going to say possible outliers at these points. So the acronym is SOX, and that's shape, outliers, center, spread. And the other thing I would say is context. Meaning anytime you're discussing a distribution or you're analyzing a distribution, you have to do it in context of what the data is that you're talking about. You can't just abstractly talk about the data. And so when I say context, I mean just adding units onto your discussion, okay? So like in describing, let's say, distribution A, I would say, the distribution of temperatures in city A is roughly symmetric, centered over approximately 85 degrees, with a spread from, it looks like, right, 72 to 104 degrees. And no indication of possible outliers. So in each discussion, in each part of my discussion, I was referencing that these are temperatures in units of degrees. And I made sure to cover shape, symmetric, center. I said roughly what, 82? I was probably a little off, probably more like 88. Spread, I discussed the min and the max. We're going to talk about different measures of spread. And then I said there don't seem to be any potential outliers. All right, so let's discuss something more specific. Describing shape. A distribution is roughly symmetric if the right and left sides of the graph are approximately mirror images of each other. It's skewed to the right if the right side of the graph is much longer than the left, and it's skewed to the left if the left side of the graph is much longer than the right. I have a trick for the skew. If you think of looking down at your foot, and your foot has the shape like big toe, smaller toe, smaller toe, smaller toe, smaller toe. That's your right foot from a top-down view. The perfect drawing of a foot, looks like a photograph, I think we all agree. So your right foot has a right skew. And then your left foot, again, big toe, smaller toe, smaller toe, smaller toe, smaller toe. And so your left foot would have a left skew. So that's how to remember it. But the general idea to remember, the right skew tails off towards the right, the left skew tails off towards the left. All right. So a couple different shapes I want to describe. Symmetric. So symmetric, a lot of times in statistics we think of this bell-shaped curve because it's a very special curve in statistics, but it doesn't have to just have one peak to be symmetric. It can be bimodal and still be symmetric, or it could be uniform and still be symmetric. Uniform is when every value is taken the same number of times. All right, so skewed right means you have a clump on the left and it tails off towards the right. Skewed left is the opposite, tails off towards the left, but you have a grouping of data on the right. Unimodal, that means here's your horizontal axis. All data is taken the same amount of times. Oh no, I'm sorry, that's not unimodal, that's uniform. Unimodal just means one peak. Oh. So all three of these are also unimodal. Whereas bimodal means two peaks. So that one's bimodal and symmetric. Again, it doesn't have to be bimodal and symmetric. One peak could be taller than the other. Bimodal just means two peaks. And then uniform means all data, the frequency is taken the same number of times. So it just ends up looking like a flat line. Sorry, my picture is covering that. There you go. All right. So here are the number of calories per serving for 16 brands of frozen cheese pizza along with a dot plot of the data. Describe shape, center, and set of the distribution. Are there any outliers? So remember the acronym. We remember to make sure we cover all of our bases as SOX plus context. Okay. So I kind of drew the rough density curve. I drew my peak a little high there. It probably doesn't need to be that high. But I said the distribution of frozen pizza calories is roughly symmetric, centered around 330 calories with a range of about 120 calories. There's a possible low outlier of about 260 calories. Now you might have said that the shape kind of has a slight left skew. I would be okay with that, but if you consider this a possible outlier and you want to eliminate its contribution, other than the outlier, it is roughly symmetric, I would say. But either one of those is okay to say. So remember, there's a lot of gray area in statistics, and you can use kind of a lot of gray area language, and you want to make sure to Definitives are generally bad. When we're using statistics, we use a lot of probabilities, which don't necessarily, generally don't say that something is guaranteed or that it's guaranteed not to occur, because probabilities of 0 or 1 are really rare. So I would have been okay if you said there's a slight left skew. And that 260 is really on the edge of even being an outlier. It's not that far of a deviation from the regular pattern. Everything else, like the center, I'm just eyeballing what I think is roughly the center of that distribution. And range is just the maximum minus the minimum value. So you could have also just listed the maximum and minimum value to discuss spread. But you just want to remember complete sentences, and make sure you provide context along with shape, center, spread, and outliers. All right, the other thing you'll be asked to do is compare two distributions, and just some mistakes when students are asked to compare two distributions is what they do is just describe the individual distributions separately, when really you want to be using comparative language, specifically comparing the center and the spread. So talking about which center is greater than or less than the other and which spread is larger or smaller. The shapes, you are just going to kind of discuss them individually, but those centers and spread need to be actually compared using comparative language. So here's an example of energy cost of top versus bottom freezers. So when I say top versus bottom, I mean literally the type of fridge that has a freezer on top and the type that has a freezer on the bottom. So we can see the difference in distributions here. So bottom freezer energy cost versus top freezer. And if we're asked to compare the annual energy cost between those two distributions, here's an example of an outlier, or sorry, of a solution to that. So it says the distribution for bottom freezers looks skewed to the right and possibly bimodal. So they say possibly bimodal because, again, if we draw a smooth curve over here, probably something like this. It's not extremely bimodal. But again, using that kind of gray area language, with modes near $58 and $70 per year. So modes are where the peaks are. We'll talk about, I'm sure you've heard mean, median, and mode before. The distribution for top freezers looks roughly symmetric with its main peak near $55. The typical energy cost for the bottom freezers is greater than the typical energy cost for the top freezers. So good, that comparative language is super important to use, especially for center and spread when you're comparing two distributions. Midpoint of $69 versus midpoint of $56, and spread. There is much more variability in energy costs for bottom freezers, so it's more spread out for bottom freezers, and they're using, again, comparative language. Outliers, there are a couple of bottom freezers with unusually high energy costs, and there are no outliers for top freezers. So that's it. So you can only really use comparative language for center and spread, but it's really important that you do so or else you would lose points. And notice all the context they give there. They're constantly discussing what the context is. These are freezers, and they're the context of the data, which is units of dollars. All right, stem plots they're almost like dot plots, but you're using the actual numbers, the data values, to create the dot plot. So how do we make a stem plot? We separate each observation into a stem, all but the final digit, and a leaf, the final digit. We write all possible stems from smallest to largest in a vertical column and draw a vertical line to the right of the column. And then we write each leaf in its own row to the right of the stem. Arrange leaves in increasing order out from the stem and provide a key that explains the context, what the stems and the leaves represent. All right, so step one, a stem is everything but the final digit, and a leaf is the final digit. So let's look at an example of this. So this is a sample of 14-year-olds from the UK that was randomly selected using a census at school website. And these are the heights of the students in centimeters. And we're going to make what are called back-to-back stem plots to compare the distribution. So here's two ways I can make a stem plot for male heights. So one way to do it, we're going to use all but the last digit for the stem, meaning 154, all but the last digit is the stem. So the 15 is the stem, and the 4 is the leaf. And then we're going to take the data, and you want to do this in increasing order from closest to the stem out. So you're going to go through and find the smallest number first, which is 151. So the 15 becomes the stem and the 1 becomes the leaf. And so that's the first number in our stem and leaf plot. And so you draw a vertical line between the stems and the leaf. So that represents that 151 centimeters. The next smallest number is 154. So the stem is still 15, but the leaf is now 4. So this data represents 154 centimeters. Does that make sense? And then 157. So the 15 is still the stem, but then the 7 here is the leaf, and so on. The last one is 159. And so I said this is kind of like a dot plot. It's actually like a dot plot turned on its side. So if you think of this, of rotating it 90 degrees, then it would kind of look like a dot plot where the actual digits, the leaves, represent the dots, right? For problems like this, where the data is so closely grouped together, sometimes there's one other way we can make a stem and leaf plot, and that's over here. And this is with what we call split stems. And so split stems means that you're going to split the stems and the leaves so that there's 2 stems for every group of 10 numbers. So the 150 has 2 stems. One of those stems represents 151 through 154, and the other stem is going to encompass everything 155 through 159. So they each have 4 possible leaves. They each have leaves. The lower stem will have leaves of 1, 2, 3, or sorry, of 0, 1, 2, 3, and 4. And the other one will have 5, 6, 7, 8, and 9. So they each, have 5 possible leaves. And all that does is kind of spread out the data and give you maybe a better look at what the true shape of the data is. All right, so that's split stems versus regular stems. A back-to-back stem plot is where we have 2 sets of data, and we put one set of leaves on one side, so I could put the men over here, and I put the other set of leaves on the other side, so I would put female on that side. And so if we use split stems, we can definitely see that even when we split stems, the female distribution has much less variability than the male distribution, right? And the males tend to be centered around, I would say, 165 centimeters, somewhere in here, whereas the female distribution tends to be centered closer to somewhere in this area, the 164, the 160 to 157 area. The only thing I'm not a big fan of with these back-to-back stem plots is that when you're looking at them, you have to recognize that the female stem plot is kind of backwards. The male stem plot, you can think about rotating just 90 degrees that way, and then it'll just look like a dot plot, and it'll be formatted in the correct direction. But the female, you can't rotate this way 90 degrees because it would be, the x-axis would be going the wrong direction. So you kind of have to think about it rotating it and flipping it if you wanted to view it as a dot plot. All right, that's it. We'll work on the problem set for 1.2.1 in class.